morning, everyone. I'm Hakan, and today I'm going to talk about a scalable UI architecture that we've been exploring since the beginning of last year. And this architecture is based on the idea of composing view models, and we call this architecture as micro-feature architecture. The idea behind this architecture is about transforming the way we manage complexity in our views and view models. Instead of large monolithic structures, we break them into smaller, self-contained, portable business components, which are called microfeatures. So, before starting, I'm working as an Android engineer in Delivery Hero, and our company is present in more than 70 countries. Its mission is to deliver anything straight to customer stores. And our team in Delivery Hero is responsible for developing the rider application for all these brands, and all the applications are actually different branding of the same rider application. They share the same source code. Main functions of the rider application is to allow riders to determine their working hours, start working, accepting to orders, performing their delivery tasks, etc. And last year, there has been a major change in our app's scaffolding, initiated by our designers and product team. Because of this critical change, we needed to invalidate our existing UI architecture from technical perspective. Let's take a look at this major change before diving into technical details, and let's revise what the design change is. So here, these screenshots are from the old design of our app, where we have dedicated tabs for each main functionality of the app. The status tab here is for determining your working hours, starting to work. Deliveries tab is for delivery tasks, etc. And all these functions were totally isolated from each other in different tabs, and they were owned by different teams. I think this is a critical point as well for the architecture. And after running several user studies and competitor analysis, our product and design teams decided to move to a new UI design to provide a better user experience to our riders. And here are some sample screenshots from the new design. And our new design does not have bottom navigation as shown in the screenshots. There's no tabs. Home screen is the only screen, and it provides access to all content and features. So note that these changes are targeting actually UI only, and our source of truth for domain and data is still the same, but we are changing how we present this data to our riders in a context-aware manner. As you can imagine, this is a huge change in the app scaffolding, and also a big change from the ownership of features perspective. This change comes actually with a very critical question. How can we continue developing our rider application with 7 teams while everyone wants to show their content on a single shared screen? In this talk, we are going to propose an architecture that will help us to overcome this challenge. So, before diving into the solution, let's identify the architecture requirements needed to support this huge design shift. Depending on the new design requirements, our architecture should enable showing dynamic contextual content on a single screen. It should enable showing UI components that are backed by different data sources. It should also foster portability by enabling composition of UIs in any host. And it should also keep loose coupling between features, squads, teams, and domains. So these are the requirements, and here is our next question that we need to answer. Does our current architecture support these requirements? Let's run a very quick architecture review to answer this question. Before asking the first question of the architecture review, maybe we can go a bit back in the history of Android development. All the story actually started with activities, and we were using them to write all our UI logic, and most of the times all our business logic as well inside these classes. Then fragments have arrived. We had new classes to offload some code from activities to fragments. And after that, these MVX patterns have become very popular, and Google came up with an opinionated solution called Jetpack ViewModel. And these ViewModels were equipped with some superhero powers like configuration change survival, ViewModel scope, save state handle, etc. And actually, we found more space to write some more code. So we were just moving our code from activities to fragments, fragments to ViewModels, and then it goes like this. Of course, the story didn't finish here. New features arrived from product teams, fragments got bigger, ViewModels got bigger, and adding a new feature actually became more complex than before. Then, at this point, we started receiving some signals actually from our fragments and ViewModels. Tech debts were accumulating because we are writing more code into these, and then they are getting bigger and bigger without refactoring them. And then here, when we had these signals, our teams started to work on these tech debts, right? Unfortunately, it didn't happen for us like this, and we ended up with even bigger fragments and bigger ViewModels, which are hard to refactor and maintain, and they were ready to explode. I think this story should be familiar for some, or maybe most of us in this room, I'm not sure. It has been a very similar experience for us, and we ended up with this one. After this brief recap of evolution of ViewModels, let's answer our first question. Is it possible to use UI logic from the existing ViewModels? Since they are really coupled there, and then a very complex logic inside ViewModels, I think the answer is clearly no. So let's continue with other questions. Here's a screenshot from our old status screen. It has several UI components for different rider status scenarios. Our next question is, can we reuse these components in our new design? These components are tightly coupled with the host fragment, and they have all this recycler weave complexity, and one UI state mapper for the whole screen, which is a very complex one. And they are not written in Compose. Of course, this is not a hard requirement, but nowadays I think having things in Compose is better. And I think we can also clearly answer this question as no. And the last question is, can we reuse existing domain data layer? Thanks to our observable repositories and domain use cases that we already have before, we didn't need to rewrite our data and domain layer, and we were able to use it maybe 80–90% of the time. So after briefly reviewing our architecture, we decided that we need a paradigm shift in our future development process. So rather than creating an isolated screen and then implementing UI components specific to that screen, we are going to create self-contained host-agnostic UI components, and then we are going to build our screens using these components in different hosts. And we call these self-contained, host-agnostic, and portable UI components as microfeatures. Before diving into the details of microfeatures, let's see some example microfeatures that we've already implemented, and it will make it easier maybe to understand the concept of microfeatures. All the components here are self-contained microfeatures which can live in any host with minimal integration effort. They can populate their own content, they don't require data from their root, and they just need minimal support from their hosts. Here you can see some more examples. This is the second patch that we implemented, and recently we also integrated in-app navigation solution to our Rider app. You can see menu actual component at the bottom, and this is a very, actually, in-app navigation came up with very dynamic content requirements, and our architecture also supported that one. We have recently completed the migration of our home screen to microfeatures for both Android and iOS platforms. I will be providing actually more details about the migration process towards the end of my talk as well. So, before that, let's explore the microfeatures in detail. So, a microfeature consists of a UI model and a composable. It's self-contained and it implements its own unidirectional data flow. It provides APIs, factory methods to create its UI model and composable. It's host agnostic, needs a host to start functioning, and it fosters composition of UI models and composables. Here, actually, we need to highlight some keywords before deep diving into this microfeature definition. So this one of them is UI model, the other one is unidirectional data flow, provider APIs, host, and composition. Actually, we'll be discussing all these keywords in detail soon, but before that, maybe you are wondering something. I think we saw this UI model keyword in the first slide. Now it's the second time here. So what's a UI model and how is it different from a view model? Let's try to answer this question. View model keyword is already reserved by Jetpack view model library. So that's why we need to come up with a new name for our view models, and we call them UI models. Actually, view models and UI models have a lot in common, and they are very similar, but they also have some slight differences. Maybe we can compare them here. So they both populate and publish state to the UI. They react to events from UI, and they persist data through configuration changes. This is built in Jetpack view model, and actually here is the idea. If your UI model is hosted by a Jetpack view model, then you can also survive configuration changes in UI model. Jetpack view model, the Android version, is platform independent. I think now a KMP version is also coming. I didn't check it, but of course it's platform independent. And the other one, for UI models, actually it's totally platform independent. It doesn't use direct Android references. And Jetpack view model have coroutine scope access built in, and here it's the same here. If your UI model is hosted by a view model, then you also have access to coroutine scope, this view model scope, you can say. Easier test setup. I think there are slight test setup needed for Jetpack view models, but for UI models, it's a pure Kotlin. You don't need to. It's just a pure Kotlin class, a simple one. You don't need that setup for UI model tests. So after actually comparing a view model and UI model, someone can ask, are we getting rid of view models? I think the answer is partially yes and partially no. So we want to use these superpowers of view models while keeping our UI models platform independent and lightweight. So how can we actually achieve that? So here's the idea. What about creating a parent-child relationship between a view model and UI models, so that view model can pass these superpowers to its children? For example, in this scenario, we have 3 children UI models, and they are hosted by a parent Jetpack view model. In this case, if view model survives configuration changes, since it has references to UI models, they will also survive configuration changes. And ViewModel has this ViewModel scope and save state handle superpowers, its Android powers. Then Jetpack ViewModel, while creating UI models, child UI models, it can pass coroutine scope. And also we can create a simple abstraction over save state handle and then pass it to our UI models to make them platform independent. And it's similar here. Every UI model doesn't need everything else. This one only needs coroutine scope and we pass it, and the other one just needs save state repository and we pass it. These UI models are designed to be self-contained and portable. They require really only minimum integration support from their parent, like coroutine scope, save state repository, and it's just that. So we are not passing data from root to our UI models. By using these UI models, we can compose bigger view models, and we call this process as composing view models. Now, we have seen the difference between a view model and a UI model, And in one of the previous slides, we mentioned that microfeature architecture is following UDF pattern. So how can we fit our UI model into this UDF? So here is the traditional UDF, which is kind of tailored for a microfeature. The only thing that worth mentioning here is that the UDF here is a micro level UDF, which is scoped to UI component rather than the full screen. So in a single screen, you can consider that we are going to have as many UDFs as the number of microfeatures in that screen. Maybe that's a bit controversial to UDF, where you keep all screen state in a single state holder, but now we are actually shifting our perspective. We are not building isolated screens anymore. We are building self-contained components that can be used to compose UIs in any host. Soon, actually, we'll be exploring an example microfeature implementation. Before that, let's explore the blueprint of a microfeature. Here we have class diagram spanning 2 modules. These modules are API and implementation modules. This is a very common pattern to split API and implementation of features. Microfeature architecture actually follows the same pattern here. And you can see the API and implementation modules. Main components of this architecture are UI model and composable. As an implementation of UDF, UI model exposes its observable state and actions while receiving events from the UI. Composable here is receiving UI model and observing the state and actions, and when an event happens on the UI, it calls the relevant event handler from the UI model. If a host wants to show its component on its UI, then it needs to use factory interfaces, which are provided in the API module. As the name suggests, UI model factory provides UI model, and composable factory provides the composable function. Note that we are returning a composable function here, so we can invoke this function in the host and render the UI. So it's a reference to composable function. The implementation of the factories, UI model and composable, is done in the implementation module. So we are not leaking our implementation details to hosts that are using our microfeatures. They just need our API module to create our instances, microfeature instances, and start running them. After seeing the abstract definition of a microfeature, maybe we can now explore a microfeature implementation to make it more concrete. The name of our microfeature is foo. Foo is a feature that has a title, a description, and a call to action button that goes to bar. Let's start with creating our UI model interface in API module. Foo UI model has an observable UI state called foo UI state. It has an action observable to publish one-time consumable actions to UI, like showing snack bar, etc. And there is a click listener that will be called from the UI. It also comes with the factory interface here, which is required for creating the foo UI model. In this case, our UI model requires a coroutine scope from the parent, and that's it for interface declaration. Let's briefly check our state and action data classes. We have unavailable state, loading state, and available state. And we also have foo action for one-time consumable actions from UI model, for example, navigating to bar and showing errors on snack bar. And here is the implementation of this UI model in the implementation module. After defining the interface, now we are going to implement it. And UI model receives the dependencies to populate its content here through constructor. The implementation of the UI model factory is done by assisted factory from Dagger, so we don't need to write boilerplate code ourselves. Of course, this is not a hard requirement. This is just an implementation detail. You can just create your own factory manually or use another dependency injection tool for populating factories for yourself. And here is these 3 dots. Let's get into that one as well. And here we show how this UI model is populating its content by itself. When it's initialized, it just starts collecting the UI state, and when UI state changes, it publishes its state as a state flow. And when an event is received from the UI like this, the state can be updated, or some side effects like go to bar can happen. In this case, we are receiving go to bar clicked and from UI and publishing an action back, because just to follow UDF pattern to be on the safe side. And we are done with defining, I think, our UI model and its implementation. Now it's time to focus on the view part, because that part is still missing. And we also have an interface, as mentioned in the blueprint, for our composable factory, which is called Foo Composable Factory. And as expected, it just returns a composable. But what's composable? What's actually Foo composable, and how we can return a composable, right? Maybe you are wondering this one. Actually, what we are returning here is a higher order function, and this function has a signature as other functions, and it's defined by a type alias, so it's easy to maintain. So this saves a lot of boilerplate code, and when we add a new parameter to our composable, then we just need to change this type alias. Note that here we are just returning a function reference that will be called on the target host via invocation. So after it's invoked, it will be rendered in the host. So we are not rendering anything else here, just returning a function to be called by the host. And let's implement our composable factory for Foo. This implementation will also be done in the implementation module. We override the create function using our type alias. And just to mention it again, here we are returning a lambda function. We are not calling the composable, but putting it inside a lambda function that will be called on the host side while rendering this composable. I think this is one of the critical aspects of our micro feature architecture. This allows us to keep the composable implementations in the implementations module while allowing hosts to access them through factories from API modules. Let's dive one more level down and see our composable implementation. As you can see, it's just an ordinary composable. It receives the arguments that are passed from the factory. The action handler disposable effect is a special construct in our code base. It's used to handle one-time consumables, so it's nothing special, and you can use any other way of consuming actions. And it's an opinionated implementation and nothing to do with microfeature architecture, but I just put it just to make it a working example. And this piece of code shows how we observe the UI state and render the content for the Foo component. Since we have 3 different UI states, we need to handle all of them here in an exhaustive manner. Here, we are showing nothing in unavailable state, and loading UI is just skipped for the sake of time. But let's maybe briefly look into this content of available Foo state. And as you can imagine, nothing special here, just adding some text and button components in a column layout, and that's it. So now we have our UI model, composable, and provider APIs ready for our Foo micro feature. But how can we actually display this micro feature? Everything is ready, but we need something to show, to display this micro feature. So this is the next question we are going to answer. How can we display this micro feature? To answer this question, we still need to define some more things, and here it's the host. So micro features cannot start functioning without hosts. So app scaffold is composed of multiple hosts, and each host uses microfeature factory APIs to populate its content. Hosts as containers may define rules to lay out microfeatures. Here, let's identify the hosts together. This is the map host, and we also have floating layer host, which is actually above map layer and populates the floating buttons and other buttons on top of map. We have this bottom sheet, which is the primary content provider in the home screen, and the most critical information is shown here. And we also have a nest. When you click on the bubble in the middle, then it opens this nest host, which shows the secondary content, secondary in terms of importance and priority. For example, if this bottom sheet host wants to show our full UI component, then it needs to use factory APIs to create UI model and composable and bind them so that they can start functioning. Now let's explore how a host can use these factory APIs and display a micro feature. Let's start from the root host, which is the home screen. Home screen has its own view model. And I think it's important to note that this is the only Jetpack view model that we have in our home screen. As micro features, hosts also have factories for their UI models and container composables. For example, bottom sheet UI model has its own factory. Its bottom sheet is a host, and bottom sheet UI model is a host UI model and has its own factory. Home view model uses this factory to create an instance of this bottom sheet host UI model. Similarly, we also have UI models for map and floating layer hosts. Actually, what we are doing here is that we are composing our home screen using these host UI models. I think the picture will be more clear if we go one level down in the hierarchy and see what's inside bottom sheet UI model implementation. So it seems that bottom sheet wants to show 3 UI components as a content, 3 micro features, we can also call it like that. These UI components are implemented using the micro feature architecture, So bottom sheet UI model can depend on the API modules of these micro features as it receives it through constructor, and create respective UI model instances as shown below. It's exactly the same method how we composed our host in the parent in the home view model. Now we are composing our content in bottom sheet in a similar way. Let's see this hierarchy on a diagram. Here is our UI model tree. We have foo, bar, and buzz micro feature UI models. And using them, we are composing our bottom sheet UI model, which is a host UI model. Foo, bar, and buzz are being used to compose our bottom sheet UI model. All these 3 host UI models are used to compose, and also here, if we continue one level up, bottom sheet UI model, map UI model, and floating layer UI model as host UI models are also used to compose our home view model. This is composing UI models part, and the view part is still missing. So how can we actually integrate our composables into this tree? Let's check that part. So here it is for bottom sheet. We have a composable host for the bottom sheet. It's just a container. It receives all factories for micro feature composables and also some functions that are needed to be provided by the host, like showing a snack bar, etc. Like here. Inside the host, we are calling micro feature composable factories to create composable function references. And here, when we call the create function, we are not rendering anything, but we are just getting a reference instance of the function. In order to render that content, we need to still call the function returned by these factories. Here we are using remember just to avoid creating these functions again and again when a recomposition happens. Afterwards, what we just need to do is to invoke these functions so that we render the content. And actually that's it. We bound our UI models and composables in the host, and they started functioning, and now they are visible on the screen. Now let's revisit our composition tree to see the whole picture. So our bottom sheet content, the host, is bound to bottom sheet UI model. foo composable is bound to foo UI model and similar for bar and buzz microfeatures. And home activity is bound to home ViewModel. So we have an activity in the end in our application, and then our home ViewModel that we've shown in a couple of slides back is bound to our home activity. Actually, this is the whole picture of our composition tree, which shows the binding of UI models and composables. And now we want to, I want to actually talk about another concept here, because maybe you observed that maybe this could be not scalable in some cases. We have seen integration of microfeatures into host, but as the number of microfeatures grows, then footprint of integration in host also grows. If a host is not that much generic and just hosts 3 microfeatures like this one, maybe everything looks acceptable from complexity perspective. But what if our bottom sheet is a generic one, and like in our rider application, and it just wants to show, I don't know, tens of different microfeatures depending on different context of rider. Then our bottom sheet host, then our bottom sheet host becomes, of course, quite complex. I just put 5 here just to make it complex, but you can imagine if you have 20, 30 microfeatures that's possibly shown in that bottom sheet, then your class will be, again, very complex. It will not help with anything else. I think then here we need to answer another question. Is this solution scalable? So I think there's a way to make our solution scalable with some small abstractions. First abstraction is item UI model. Every UI model actually implements this interface and communicates to its host whether it's displayable or not. And second abstraction is the configuration. Configuration is just a logical group of item UI models. For example, for the rider application, it could be working configuration or non-working configuration, etc. Configuration enables to group item UI models logically depending on business domain. Depending on meta state changes like non-working to working state, okay, everything is there. Let me continue. Depending on meta state changes like non-working to working state, get bottom sheet configuration publishes new configuration. So we are observing this one. When we observe this new configuration, then we unregister item UI models from the old configuration and register the ones from the new configuration. Please note that an item UI model can be registered by a configuration, but still it controls its displayability by itself because we have item UI is displayable field there. Even it's registered, it can communicate whether it's displayable or not to its host. Host UI models, actually, responsibility is just collecting displayable items in the current configuration and publishing them to the UI as its current state. So now, in bottom sheet UI model, we don't have direct references to any microfeature, but we are doing it through an interface, which is an item UI model. Let's visualize the new configuration concept. We have 2 configurations for the bottom sheet. We can think configuration 1 is for non-working state and has 3 item UI models registered. And in a similar manner, we have configuration 2 for working state, and it also has 3 item UI models registered. And as you can see here, configurations can also share some item UI models. Here, I think shared one is the full UI model. Let's see configuration changes in action. So our context changed. We received some data from our backend, and our configuration 1 is now the active configuration. Now we are showing bar, buzz, and full microfeatures in our bottom sheet. Then another context change happened. We are now, the active configuration is now configuration 2. It's working state, we can call it. And we have full UI model, X and Y UI models. So full UI model is still there, and it's still staying, but we just unregistered bar and buzz UI models, and X and Y UI models are registered because they are also part of configuration 2. Now, actually, we have seen the concept of microfeatures and an example implementation. let's have a look at some aspects of this architecture in a broader level, so that we can see what it's enabling for us now and what it can enable us for the future. One of the aspects, actually, this is also mentioned in previous slides. The first one is portability. Let's say we have a scenario where we are showing these components in our home screen. Then our context changed, triggered some UI changes in the screen. So another host became accessible. Let's call it Nest. And this host is for showing the components which have secondary priority, while bottom sheet is showing the components that have the highest priority. And here, bar and buzz actually becoming less important in this configuration, in this context. So we are moving them to Nest host, and they start functioning there without any need for any data context from Nest. And X and Y macro features are arriving because in this context they are more important, and we are just registering it to bottom sheet, and they start functioning. So micro features are portable. You can just plug and play them in any host if it's compatible with the host, of course. Another aspect is that it's easier to move UI logic to multi-platform with this solution, since we have a clear distinction between platform-dependent Jetpack ViewModel and our UI models. This implementation of micro feature makes it easy to move our UI logic to KMP. The root host should be platform-specific, but all UI models can be implemented using pure Kotlin without depending on any Android library. In some parts of our rider application, we have server-driven UI implementations, but our application is not fully implemented with server-driven UI now. While designing micro feature architecture, we always kept server-driven UI compatibility in mind, so that if you want to if you want to switch to server-driven UI in the future, our architecture should not be the blocker. So how can we configure our micro features with a remote UI configuration that is received depending on user's context? So let's follow this flow here. Context changed, we received a configuration from backend. We persisted in our observable repository. It has two types of data. One of them is remote layout configuration. Host is actually interested in this data, and we have our micro features. And these are actually interested in component configuration, the data, business data, they just want to show. Our host actually creates micro features depending on the remote configuration that we receive from backend, and micro features themselves start functioning, listening these component configuration from the repository. And you can easily actually implement micro features with a server-driven UI solution. Another aspect is testability. I think we shouldn't miss that piece as well. So it's a normal, we are using actually unit testing, screenshot testing, integration testing, and end-to-end testing for testing our micro features. Generally, the scope for unit testing is micro feature UI models, UI logic, repositories, mappers, etc. For screenshot testing, micro feature composables, as you've seen before, we are just using screenshot tests for the static behavior of micro features. For integration testing, for the interactive parts, button clicks, text fields, and other stuff, we are using integration testing, and these are also living in the implementation module in Android test folder. And when it comes to end-to-end testing, we create a host and put several micro features inside that host and create a flow and actually write our end-to-end test using this one. So this is how we generally test our micro features. And after providing detailed explanation of micro features and talking about their aspects, now it's time to talk about some learnings. Let's go over some of them here. And a micro feature should be a logical group. It should mean something from business domain perspective. So it's not a good practice to oversplit the features into several micro features if they are not meaning anything by themselves. Similarly, it's better if we keep our UI model hierarchies depth in control and prevent having unmaintainable hierarchies. I think this is also key. And another critical point is that we should always keep host independence in mind, so that our micro features should require a as less as possible from their hosts. I think this is also very critical. And we are almost there. We have just 1 minute. I will just make it quick. Before ending the talk, let me present some numbers about our microfeatures journey up to now. Here is the current state. We have 75 microfeatures, more than 75 microfeatures implemented in 6 hosts, and these are delivered by 7 cross-functional teams, and 30 mobile engineers are working here. With this configuration, teams can deliver features for the home screen independently, and our teams are quite happy with the new architecture until now. And microfeatures first implemented by Android starting from the beginning of 2023, and after its success, it's also adapted by iOS Rider application. They have just finished the migration to microfeatures recently. And after actually having this alignment, it actually enabled us to have a common language between mobile platforms as well as design and product teams when we are talking about components. In addition to this, it created a foundation for us to move forward with fully server-driven microfeatures. So it's the next topic on our table. Here's the QR code that takes you to Delivery Hero Tech blog about microfeatures. And thank you for listening. I think there's no time for questions, but we can talk here together if you want. Thank you.